Hey, what's up, dudes? Welcome to the first episode of Enlighten Me. Today, we begin our journey toward discovering the theory of everything, the holy grail of physics. The theory of everything is the fundamental framework of physics, which explains and links all physical phenomena in the universe, including particles, light, gravity, and possibly even time. It's considered not only the greatest unsolved problem in physics, but one of the biggest and most important mysteries in all of existence. Because if we could solve the theory of everything, it would most likely lead to solutions to many other mysteries as well. Now, in order to understand where we're going on this quest, you must first understand where we are. It's going to be a wild ride. Our journey begins now. Okay, I'll begin with a quick general overview of the sort of ideas that are currently perpetuated in science today. If what I'm saying doesn't make sense at first, don't worry. I'll go into more detail later as we cover each subject individually, so bear with me. Also, not everybody pushes all of these ideas, but these are the most popular ones. The conventional narrative in physics goes something like this. 13.8 billion years ago, the universe began with the Big Bang, which is evident by rewinding the expansion of the universe. At first, all of the energy in spacetime in the entire universe was contained within an infinitely dense point called a singularity. Immediately, space inflated by a factor of at least 10 to the 26th power, that's 1 with 26 zeros behind it, in less than a trillionth of a second, potentially driven by the inflaton field. There are four fundamental interactions, or forces, mediated by force-carrying particles called bosons. There's the strong force, which is carried by the gluon, the weak force, which is carried by the W and Z bosons, electromagnetism, which is carried by the photon, and gravity, which is mediated by a condensate of the Higgs field and of the pion field, or by hypothetical gravitons. They don't really understand how gravity works on the subatomic scale yet. On the smallest scales, things are made up of tiny vibrating strings and governed by the laws of quantum mechanics, where matter is simultaneously both a wave and a particle, acting based on probability waves and observations. There are many different types of particles in existence, at least 18, and each of them are excitations within their corresponding fields, which permeate the entire universe, meaning gluons manifest in the gluon field, the Higgs boson manifests in the Higgs field, and so on. Particles are constantly popping in and out of existence in empty space through quantum fluctuations, and when mediating forces through virtual particles made of energy, which can neither be created nor destroyed, but is simply borrowed and returned before a measurement of it can be made, so that it doesn't violate this conservation law. Both matter and antimatter were created in equal quantities and annihilated each other, leaving just one matter particle for every billion matter-antimatter particle pairs. After cosmic inflation, the expansion of the universe slowed down drastically, but 7.7 billion years later, the expansion began accelerating again, due to a mysterious dark energy. Furthermore, the universe is filled with clusters of invisible massive particles called dark matter, which only reacts with normal matter through its gravitational pull. In fact, normal matter makes up less than 5% of the universe. The remaining 95% is composed of roughly 27% dark matter and 68% dark energy. When a star collapses, and its matter condenses enough that the escape velocity of its gravitational well exceeds the speed of light, it creates a black hole singularity. Lastly, time is relative rather than being the same everywhere, or absolute, and it is caused by an increase of entropy. That's just the tip of the iceberg, but it's a lot. Now, naturally, I'm eager to just come right out and reveal where my intuitions have led me away from that conventional narrative during my studies. But just in case you're a big proponent of that narrative, maybe not all of it, but even just some of it, I don't want to scare you off before I've had a chance to make my case. However, I will tell you this much right now. I believe that out of that entire list, only 3 things, maybe 4 at most, will survive the quest to discover the theory of everything. Believe it or not, the rest are probably false. Just misinterpretations stacked like an upside-down pyramid upon a crumbling foundation. And to be honest, I'd be willing to bet nearly everything I own on that. There was a time when I believed in some of the things on that list, or rather, I was told that they were true and I hadn't bothered to give them much thought. Physics just wasn't an interest of mine yet. I figured, who am I to question professional scientists? They know more about those subjects than I ever will, so if they say they're uncontested facts, then maybe they are. What do I know? But my trust in that conventional narrative ended once I began my personal crash course in physics. It all began the day I looked up the evidence for the Big Bang. I thought, that's it? That's nothing. You might be thinking, well, if the evidence for the Big Bang is so minuscule, then why do so many people believe in it? Let's follow the logic, shall we? There are 4 main pieces of evidence to support the Big Bang: the evolution of the universe over time, the cosmic microwave background radiation, or CMB, the distribution of elements, and cosmological redshift. The evolution of the universe over time is pretty straightforward. The further out into the universe we look, the further back into time we are seeing, because light takes time to travel. However, evolution over time is really only evidence that the universe had a beginning, not that that beginning was the Big Bang. You can have a beginning without the Big Bang, so don't mistake evidence for one as evidence for the other. The universe changing over time is not inherently dependent on the existence of the Big Bang, so it doesn't count. Next, the CMB is the earliest light that we observe, which indicates the universe's temperature at the time it was emitted. It's often used as evidence to support the Big Bang. However, the CMB shows that the universe used to be almost completely evenly distributed. In fact, it's so uniform or isotropic that it's actually a problem for the Big Bang. This is called the horizon problem. The average temperature fluctuations in the CMB is about 18 microkelvin. I know most people don't really know what that means. It means the variation is extremely subtle, roughly 1 part in 100,000. Displayed without the exaggeration that we're typically shown, the CMB looks more like this. Completely uniform. And this doesn't fit well with the Big Bang theory. So, in an effort to try to save the Big Bang, they had to invent an additional theory to add on to it, called cosmic inflation. Inflation is the idea that space expanded extremely quickly and greatly for just a fraction of a second immediately following the Big Bang, so as to smooth out the universe. Remember those really big numbers I showed during the conventional narrative? That's inflation. After which the universe expanded much more slowly. However, the mechanism of inflation is entirely unexplained. They've never come up with any real explanation or mechanism for how it started, how it stopped, or what caused it. It's just a band-aid on a big crack in the theory invented in an attempt to salvage the Big Bang. And the CMB is not dependent on the Big Bang. Even in the traditional theory, it came from a time about 380,000 years after the Big Bang. And like evolution over time, the CMB is just evidence for a beginning of the universe. But in its current state, it's actually evidence against the Big Bang more so than it is in support of it. And third, the distribution of elements in the universe, meaning the abundance of light elements, mostly hydrogen with some helium and lithium. Again, that doesn't require a Big Bang either. You can have the same ratio without the Big Bang. There's possibly issues with the predicted versus observed ratios of elements anyway, which is why it's used as evidence for the Big Bang as often as evidence against it. So it's hard to count that one. Plus, essentially the entire process that produced the elements occurred post-inflation and actually has no direct dependence on the existence of the Big Bang. I'll explain why in a minute. And lastly, we have redshift. Now, redshift is the primary piece of evidence for the Big Bang, and without it, I don't believe anyone would have ever come up with the Big Bang. As we look out into space, the light we receive from distant objects is shifted toward the less energetic end of the light spectrum, the redder end, hence redshift. And it doesn't matter in which direction we look. This shifting of the light was interpreted as being caused by motion away from us as the universe expands, causing the light waves to stretch, similar to the Doppler effect, which is a change in the frequency of a wave in relation to an observer who is moving relative to the source of the wave, like how the pitch of a siren on an emergency vehicle changes as it passes you. And if the universe is expanding, then if you rewind the clock back, at some point in the past, the universe must have been unexpanded down to a single point, which was the Big Bang. Furthermore, not only is the light from distant objects stretched fairly consistently relative to the amount of distance that light has traveled, but the rate of its stretching is increasing over time. The light is arriving fainter and redder than expected, which causes it to appear as if the rate of expansion is accelerating. The conventional narrative asserts that this accelerating expansion is caused by some mysterious dark energy, which is just some hypothetical substance that has no explanation or additional evidence, but that's the subject of my next video. Additionally, according to the redshift of the most distant objects and what recessional value that would equate to, the far reaches of the universe are moving away from us faster than the speed of light, which exceeds the cosmic speed limit. Well, not just the far reaches of the universe, an estimated 94% of the galaxies in the observable universe are moving away from us faster than the speed of light, and presumably everything beyond the observable universe. Cosmic inflation, which I mentioned earlier, also caused the universe to expand faster than the speed of light. They get around this by saying that you can't move through space faster than the speed of light, but objects moving as the result of the expansion of space don't have to obey this law because they're not really moving. The speed limit only applies to objects in space, but not to space itself. I mean, I get it, but the solution just seems like kind of a cop-out. Additional evidence used to support cosmic expansion includes the cosmological principle, which is the fact that the universe is isotropic or evenly distributed, and homogeneous, or has roughly the same distribution of elements across the observable universe, and the Copernican principle, which is the fact that the same sort of observations could be made regardless of the observer's position, which is used to argue that we are either at the center of the universe or the universe has no center from which the universe is expanding. However, the cosmological principle could apply equally as well to a universe that began in an expanded state. And there's another answer to the Copernican principle, which I'll reveal after we cover the evidence against the Big Bang. First, we have baryon asymmetry, or the missing antimatter problem. Allegedly, the universe should have produced equal amounts of matter and antimatter, but this obviously doesn't seem to be the case. It's considered one of the greatest mysteries in physics, along with the origin of electric charge. But that's assuming we understand the difference between matter and antimatter, and what electric charge really is. It's clear to me that we don't, and I will argue that later, but that's an issue for the episode on electric charge. So, to be fair, I'll just cross that one off for now. Then we have the problem of the missing magnetic monopoles. This just demonstrates a clear misunderstanding of how magnets work. But again, that's an issue for the electric charge episode. While the missing magnetic monopole issue is related to the Big Bang model, I don't see it being entirely dependent on the Big Bang, so I won't count this one either. That's fine. Like with redshift, I want to focus on the hard evidence that would really indicate something major, the big guns. Next, we have the existence of structures too large to have formed in the time since the Big Bang, and too far apart to have ever been in communication. This is actually part of the previously mentioned horizon problem, which applied to the CMB, so I'm not going to count it separately. But it's worth mentioning since it is actually a problem for the Big Bang theory. Then there's the flatness problem, which is considered a cosmological fine-tuning problem, meaning that it has a measured value so close to what it needs to be in order for objects to form and for life to exist that scientists can't explain why it has the value that it has and not some other arbitrary value. The flatness problem refers to the density of matter and energy in the universe, which affects the curvature of spacetime. There's a critical value required for a flat universe, and any deviation in the past would increase rapidly over time, leading to massive curvature today. But in order to get a universe as flat as the one we have, the density of the universe in the past would have had to have been even closer to the critical density than it is now, departing from it by 1 part in 10 to the 62nd power or less, in order to have essentially no deviation in the current universe. That is a problem, so we'll keep that one. Also, if the distribution of galaxies were determined by quantum fluctuations in space closer to the time when the universe was a singularity, as the traditional narrative suggests, you'd expect them to be distributed more randomly than they are, right? Then there's the discrepancy between measurements of the speed that the universe is expanding, called the Hubble constant, using the CMB versus Type 1a supernovae. This discrepancy is called the Hubble tension. Given the accuracy of the measurements, this suggests something fundamentally wrong with the theory behind the measurements. And this may be a problem, but not one as critical as some others. The Big Bang also violates the first law of thermodynamics, which states that energy can neither be created nor destroyed. But unless the universe is eternal, at some point, that one's kind of unavoidable with or without the Big Bang, so I'm not going to count it. Then there's the lack of galaxy mergers in the early universe, which is supposedly part of the mechanism of galaxy formation along with black holes. They can't figure out how galaxies could have grown so massive without more galaxy mergers, or figure out if the black hole came first or the galaxy. It's a chicken or the egg thing. Then there's dark matter, which is supposedly an invisible massive particle that plays a role in galaxy formation, but it has never been found. I'll go over dark matter in the next episode, and black holes a few episodes later. But you can theoretically have galaxies form with or without galaxy mergers, black holes, or dark matter, and still have the Big Bang theory remain intact as long as some other evidence supports it. So I don't see that evidence as crucial. Like I said, I'm looking for the evidence that really means something. Then there's possible issues with the surface brightness of distant objects? Maybe. And some people think that the fact that the universe isn't expanding inside of galaxies is good evidence against cosmic expansion. But scientists get around this by saying that space doesn't expand in gravitationally bound systems like galaxies. And then there's the clumpiness problem, or S8 tension, referring to how the universe is less packed together than predicted, which conflicts with lambda cold dark matter cosmology, which is a mathematical model for the Big Bang theory, containing ordinary matter, and dark energy. But it's possible for the measured values to be one way or the other and not really destroy the idea of the Big Bang. Anyway, there's just a lot of problems. That's not even all of them by any means, but those are the main ones. So, with all that said, if we're really being honest and just focusing on the real make-or-break evidence here, the points stand at one piece of evidence truly in favor of the Big Bang, which is the expansion of the universe, and at least 4 pieces of evidence against it, or rather, 3 against the Big Bang and 1 specifically against the expansion of the universe, which is the primary evidence for the Big Bang. Those 4 things being the flatness problem, the Hubble tension, the horizon problem and its reliance on the unexplained cosmic inflation, and the expansion requiring a method of expansion, which is supposedly the unexplained dark energy. I definitely see inflation and dark energy as noteworthy problems here, not as solutions. There is no evidence for inflation or dark energy beyond the reasons they were first hypothesized, which was to force our observations to conform to conventional theory, rather than letting the evidence against the Big Bang remain as evidence against it. Regarding redshift, nearly all astronomical objects are so large and distant from us that visible change in their position, proper motion, is barely detectable. So to measure the velocity of objects outside of the Milky Way, motion is inferred indirectly from a shift in the wavelength of its light. A light's wavelength is determined by the frequency of its wave, or its energy density. When light is stretched or emitted as the object moves away from the observer, the light wave's density decreases, and so the distance between waves lengthens, which is referred to as redshift, because red is at the less energetic end of the spectrum of visible light. Likewise, when light is compacted or emitted as the object approaches the observer, its wavelength is shortened, which is referred to as blue shift, because blue is at the more energetic end. Most of the objects we observe in space are redshifted, which, as I said, is interpreted in the conventional theory as indicating that nearly all objects are moving away from one another, which, in turn, would indicate that the universe is continually expanding or stretching in all directions. Cosmic expansion is the primary evidence for the Big Bang, since if everything is continually moving away from everything else, then, if you rewind the clock back, everything gets closer together until, sometime in the distant past, it was all gathered into a singularity at the beginning of time, the moment of the Big Bang. Also, the more distant the object, the more redshifted its light, which was interpreted as indicating that the rate of cosmic expansion decelerated until about 4 billion years ago when it began accelerating, and is still doing so, which many scientists claim is caused by a mysterious dark energy, which exerts a negative repulsive pressure propelling the expansion. You may be surprised to learn then that redshift is the only piece of evidence that could be interpreted as indicating cosmic expansion. And without redshift, scientists never would have concluded that the universe is expanding, and in turn, that it began with the Big Bang. So if redshift could be explained by being caused by something other than an object's motion away from the observer or the expansion of the universe, and that explanation matched the experimental data, the theory of cosmic expansion would collapse, and we could finally say, bye-bye Big Bang. The Big Bang and inflation don't seem to provide any additional function after they took place. So if we remove them from our historical narrative and began with a universe that is already spread out, it seems that everything could still work the same, especially if the universe is not actually expanding. Naturally, you should be able to see by now that if there is a problem, which there seems to be, then it likely stems from incorrectly interpreting redshift as being caused by the expansion of the universe. That one piece of evidence for the Big Bang, redshift, is where things all went wrong. That is the single biggest point of failure, and all issues with the theory are pointing to that interpretation. It is used as an explanation for our observations, yet it appears to be the piece of evidence least compatible with our observations, and so its existence creates the most conflicts and production of unexplained mechanisms. But how could that be? Is redshift not caused by the expansion of the universe? Holding to that interpretation seems to be problematic, as I've explained. Look, I understand that a lot of people don't want to give up the idea of the Big Bang without first finding an alternative that matches all of our observations. Now, some people have suggested alternative interpretations for the cause of redshift, such as tired light, decreasing speed of light, increasing mass of particles, shrinking particles, or tachyon plasma fields. Tired light is probably the most well-known alternative currently, but that hypothesis is considered inadequate because light losing energy as it travels would allegedly cause light scattering, which would cause distant objects to appear blurred, but that's not what we observe. With tired light, higher energy light like blue light should fade more than lower energy light like red light, but they are shifted equally. Also, with tired light, an object's surface brightness should be constant, yet it diminishes with distance. Not to mention that there's no generally accepted mechanism for how light loses its energy in tired light. That's not to say that mechanisms haven't been proposed. I've listened to many YouTube videos from people who hold tired light as their preferred interpretation. However, that is not my preferred interpretation. There is one superior interpretation that seems to fit our observations without contradiction or the need to invent unexplained mysteries like what is done with cosmic expansion. One thing that seems to have led us astray is associating redshift with the Doppler effect, wherein waves are compressed as the object emitting those waves moves toward you and stretched as it moves away, which I described earlier as being analogous to a siren on an emergency vehicle. But I don't think that's what's happening with redshift. The real cause appears to be one that I've personally never seen suggested before. My idea could be completely wrong, but the way I see it, the conventional interpretation is only partly right. They were right when they interpreted redshift as the result of light waves being stretched as they travel through space that is stretching, yes. But they got the direction of the stretching wrong. See, you can cause redshift by stretching light waves in any direction, away from you, toward you, sideways, upwards, downwards, any direction irrespective of the light's direction of travel, as long as the light simply becomes less dense or stretched. So which direction is the light in space stretching then? It's not stretching away from us as the universe expands, nor is it stretching toward us as the universe shrinks. Rather, it is stretching toward and through the individual galaxies, galaxy clusters, and filaments. It's gathering. Call it local contraction or circulation if you will. It's both. I'll explain. But what's really happening and why this is happening goes a lot deeper than that. You just have to know what you're dealing with physically. From what I can tell, this reinterpretation works well. In fact, this one simple difference makes all the difference in the world, since it reveals great insight into a single, simple, incredibly important underlying mechanism, an all-encompassing hidden truth that could actually solve most of the problems in physics. And I mean all of physics, not just problems with the Big Bang. I'll go into more detail about it in the next episode. If you find this stuff interesting, please give the video a like. If the universe began spread out, a very high entropy state, opposed to using cosmic inflation, this should solve the horizon problem. It would also be a solution superior to inflation in the sense that local contraction fits the data without adding a mysterious and unexplained mechanism like inflation. If redshift is not caused by the expansion of the universe, that eliminates the biggest reason to believe in the Big Bang. If there was no Big Bang, we don't need inflation to reconcile the Big Bang with the fact that we observe a universe that appears to be the same in all locations and directions, homogeneous and isotropic. We could just begin with a flat universe, post-inflation as it were, and if the universe is not expanding, then we don't require a mechanism to propel that expansion. We would have no need for dark energy, nor any reason to believe that dark energy exists. Not only that, but if the universe is not expanding, then we can't use the expansion rate as a means of getting the estimated 13.8 billion year age of the universe. We no longer need to explain mysteries like cosmic expansion, the Big Bang, inflation, or dark energy, because they don't exist and never did. If anyone tells you that the Big Bang is an undeniable fact supported by a slew of evidence, don't be so quick to believe them. It's not that cut and dry. There's a better explanation. If you suspected this was the case, or you never believed in the Big Bang to begin with, let me know in the comments. And please share this video. Share it with your friends, with your family, with your church, whatever. Because this isn't where the revolution ends. We're only just beginning. This reinterpretation agrees with the Copernican principle, the fact that the same sort of observations could be made regardless of the observer's position, which was previously used to claim that the Big Bang has no position from which the expansion began. Also, the conservation of energy is said to be broken by the expansion of space, but if the universe isn't expanding and is treated as a single closed system, then energy should still be conserved. Lastly, if the universe isn't expanding or contracting overall, that has a huge impact on the fate of the universe. There wouldn't be a heat death or big rip or big crunch or any such end. As space continues to condense and cycle, everything should just find its orbit and simply exist. Maybe not an entirely static universe, but still very static. Alright, let's summarize. Half of the evidence for the Big Bang is only evidence for a beginning of the universe, which doesn't necessarily involve the Big Bang. And the other half that is allegedly in favor of the Big Bang is neutral at best, since it doesn't actually require the Big Bang. Many of our observations are in fact incompatible with the Big Bang. That's why it needs things like inflation and dark energy. As far as I can tell, the most plausible solution to this whole Big Bang mystery is that the primary piece of evidence for the Big Bang, redshift, likely has a different explanation, dynamic space, which not only fits better with our observations, but it could explain many other mysteries as well. But you'll learn more about that as we go. Hopefully you're eager to hear the details about how and why this reinterpretation of redshift as local contraction and circulation works, and to see the evidence for it. I'm trying to break my explanations up into more digestible episodes, so if you're ready to cover that, as well as some other mysteries that the theory solves, such as those associated with dark matter and dark energy, you'll find that in the next episode. We're only just starting out on our journey toward the goal of reaching the theory of everything. Will we make it? Just keep watching and you'll find out. Don't forget to like and subscribe. I hope you feel enlightened. But we're not done yet. I'll see you in the next episode.